quickly. This semester, in the context of my analog IC design, analog CMOS IC design course, we have designed a digital to analog converter as a project. We also did a lot of other things. We designed a lot of op-amps and such. But you know, a piece, the resistance of a class is always its project. So in this video, I will mainly be talking about the project, the design procedure of the project, debugging, and the many results we got from the project. So let's start, shall we? And go to my project DAC. So let's start with the schematic, because there are actually some things I want to go over in the schematic form. As you can see, we have a classic R2R network and a buffer op-amp, a DAC architecture, where what's the challenge in designing that? It's a standard topology after all. Well, I will, in the next 5 minutes or 3 minutes or so, I will tell you all about the challenges in the design. Let's go over the op-amp first. I wouldn't say simplest, but our most essential components, definitely. The most fundamental, I want to say. So as you can see, we got a PMOS differential input stage. Well, input stage is always differential in op-amps, that's not a surprise. But we are using a PMOS input stage because we want our DAC output to go to accept common mode inputs as far as low as 0, and well, it cannot accept as far as high as supply voltage, but it actually can accept 4 volts. We are using a 5 volt supply here. It can work in 4 volts, so we actually have a wide input common mode range. Then we get a classical second stage, classical current source load amplifier here, and then we got a class B output stage. Well, why use a class B output stage? That is because we want real-to-real output from our op-amp. We want the output to go as far below as 0 and as high as, well, we actually want it to go as far as 4, but you know, going as far as 5 isn't a disadvantage. Then our design moves on to the DAC portion. Let's talk about some specific design considerations now. When it comes to the DAC, there are several choices to make, design choices to be made. One is the values of these resistors, and the other is the width of these transistors. Well, let me talk about both of them actually. Well, the average value of these resistors basically determines two things: your monotonicity. If your resistors are higher, you will have better monotonicity, and monotonicity means, you know, when you go from 0, 1, 1, 1, 1, 1, we have 8 bits of input, so imagine I just said 8 bits. From 0, 1, 1, 1, 1, 1 to 1, 0, 0, 0, well, the circuit, if the resistances are not well aligned, if they are not exactly equal with each other, the output may not go up, it may go down, or it might not go up at the same step as you expect. For instance, we have a 4 volt range 8-bit DAC here, so at every step we have 256 steps, and at every step we expect our output to move up 15 millivolts. So if you don't have good monotonicity, it might just move up 5 millivolts, or it might not move up at all, which is a big problem. If you choose larger resistances, you get more noise, but you actually get better monotonicity because the discrepancies, the relative discrepancies between individual resistances are decreased. We are not using an absurdly large value here. 5 kilohertz is a reasonable value, and we are actually able to make it in reasonable lengths in this process. You can see a length of one resistor is on average, 21, 22 micrometers, So it is quite reasonable. Finally, let me show you that we have constructed is the wrong word there. We have designed the layout for both our op-amp. Here you can see our op-amp layout. Just a moment there. For both the op-amp, let me show you the lower view. This is the op-amp layout design. As you can see, I put quite some time into this to make it work nicely. And well, design considerations here are to make the differential input stage symmetric, of course, and to save space, and to make resistances coming from our connections neglectable. One design consideration is the op-amp is a source resistance for the transistors, especially current source transistors here. And as you can see, their source resistances are scaled down with the actually. So when we scale transistors up in width or in gate values, we must scale their source resistance down if you want to have same source voltages. The transistors with higher widths will have higher currents, and if they have the same resistance at their source, they will have, well, in our case we are using PMOSes, so they will have lower source voltage, which is not something we desire. So we must adjust our resistors accordingly. So as you can see here, for this biasing circuit, the one with the smallest width, we have just one connection. Here we have actually three larger connections. This has the 5 times the width of this. And we have the side connections here, which actually don't do much because they are limited by these connections here. And here, which is actually this transistor, which is actually twice has twice the amount of width compared to this transistors. I am talking total width here. It has actually 6 of the same connections here compared to 5. So this is going to have the half of the source resistance, which will mean it has the same source voltage. We can actually see that in our DC analysis. We actually extract the circuit from this design and run another analysis. I will just show you that in a moment. And then let me show you the layout design of the DAC. Here at the lower view, as you can see, our designs are quite compact. Actually, this design is, let me see, 520 micrometers to 450 micrometers, which is quite small. Even in IC design standards, I have seen much larger IC switch designs. Well, but it is a simple design. But when I worked on RF designs, a chip size was standardized to, something like 1.5 millimeters by 1.5 millimeters. Anyways, there are some important design considerations here actually. As you can see, we have split the voltage sources for the digital part of our circuit and the analog part. So when the digital part draws high currents from the supply in transient switching portions, our supply of our op-amp doesn't get affected, so the op-amp output doesn't get affected. And to prevent the same thing in the ground portion, we actually made a star ground. This is our ground pin here. We actually made a star ground connection here. Well, those were all of the points I wanted to cover for today. Thanks for listening, and I hope we meet at another project soon. Goodbye. Well, it actually takes some time for me to close the stream, the recording. And I don't plan to edit it.